Hello, everyone, and welcome to our digital days. And yeah, the last session of our digital days in 2022. My name is Markus Eberle, and I will moderate this presentation. We are very pleased that you took your time to participate in our webinar and our virtual conference. The topic of today's last presentation is disinfection with UVC LEDs. Our speaker today is Dominik Köck, who is working as a product manager at Würth Elektronik eiSos. He will hold today's webinar and also answer your questions at the end. Yeah, before we start the presentation, I would quickly point out one thing. You will be muted during the webinar. That means that you cannot ask us questions with your microphone. Nevertheless, you have the opportunity to ask us questions with the chat function. The presentation will be about 30 minutes long. At the end, we have scheduled a Q&A session with 5 to 10 minutes, and there we will answer your questions from the chat. You can answer that, you can give us the question with the question function. If we are unable to answer all your questions within this time, we will answer them later on via mail, and you always can send us an email at exhibition@we-online.com. At the end of the presentation, you will be also get to a feedback survey. Of course, we would be pleased if you take the time quickly to fill out the survey and help us to improve our virtual conferences. You will also receive the link to the presentation you will see and also to the recording. And we have that also available on our website, like with our other webinars. So yeah, that's from my side. Now I wish you very much fun and good luck to our speaker, and I wish you an exciting presentation.
So thank you, Markus, for the kind introduction. Let me introduce myself again. So I'm Dominik Köck. I'm the product manager for optoelectronics and especially for UV products. And I will give you today an introduction and an overview of disinfection with UVC LEDs. So basically here the agenda is I will tell you a little bit what UVC LEDs are. So those are light emitting diodes that send out a special type of light, the UV light. And I will tell you a little bit about what kind of different UV lights there are. There's UVA, UVB, and UVC, and what the difference is. I will give you some background about disinfection. So how you can do disinfection with UV light, the working mechanisms behind it, and also some dependencies on the wavelength. And also, I will give you in the end some applications examples to see how long disinfection actually takes when you try to disinfect with UVC LEDs. Of course, disinfection with UVC is currently still a hot topic due to the corona pandemic. But I will also show you that it can and it will be in the future of a high importance, also for preventing future pandemics and general reduction of germs, for example, in medical houses, for example, in hospitals and so on. But also you can use those LEDs for disinfecting, for water disinfection, for water purification, and so on. So I will show you a few application examples for this later to tell you, yes, those UVC LEDs are here to stay even after the pandemic. And in the end, I will also give you a few notes on the safety regarding UVC. You see, UVC light is highly energetic, which means it can actually damage parts of your DNA. So this makes it very much dangerous. So you need to be careful when you design UVC LEDs in the application, but I will come to this later. So here the overview of the electromagnetic spectrum of light and UV and infrared light. So basically, you see the visible light spectrum goes from 400 nanometers to about 780 nanometers. And above this wavelength, we have infrared light. And below those wavelengths, we have UV light. And if we go to even lower wavelengths, we go to the X-rays. So for lower wavelengths, we have a higher energy. And we have basically a UVA part of the UV spectrum. We have a UVB part of the UV spectrum, and we have a UVC part of this UV spectrum. So the difference between those two or three UVC lights is simply the energy and the wavelength. So you see the UVC light is much more energetic than the UVA light, for example. And this also means that we have some different applications for UVA versus UVB and UVC light. But first, let me give you a short introduction what kind of product Würth Elektronik currently has in its portfolio. So currently we have high power UVA LEDs with a wavelength from 365 nanometers to 405 nanometers. But also since a few months now, we have UVC LEDs with 275 nanometers. There we have them in different power levels. In the future, we are also aiming to get UVC LEDs with a higher radiant flux, as those are more important for disinfection purposes. So the UVA LEDs are typically most often used for horticulture applications. You can use them for plant growing. So if you use UVA light, you can induce some special processes in the plant growth. For example, the production of a certain chemical within the plant. So you can use it for the horticulture. Then you can use it for security purposes. You can detect if you have a counterfeit build or not. But actually the most important application, I think, is the curing applications. So you can, with a UVC or a UVA light, you can cure some adhesives and glues, which is mostly used in the industry. So this is actually the most important application currently. On the other hand, the UVC light can be used for disinfection. And they are namely currently most important would be the surface disinfection. For example, you can use whatever or disinfect whatever you want. You can disinfect the surface of the masks, of your phone. You know, there are a lot of germs on your phone, much more even than on a toilet seat. So basically, this is a really nice application to simply kill off all the germs on your phone. But you can also use this in the food industry. Basically, here's an example of a few eggs. And if you have, like on those eggs, you typically have the problems of having salmonella on top of the eggshells. And you want to, for example, kill off the salmonella from this. So there have been already quite a few studies regarding this. And they found that basically you can, in principle, use UVC light to kill off the salmonella. So basically, it's quite an interesting topic to go on. But there are also like other studies that show that you can, for example, improve the lifetime or storage time of vegetables such as carrots when irradiating those with UVC light. Basically, what you do there is you can hinder the mold from forming, and this is how you improve the storage time. But I guess currently the most important application would be the air purification due to the coronavirus, which is transmitted through like water droplets in the air. Basically, there are quite a few interesting applications here where you simply have a filter in a ventilation device, and on this filter you shine on some UVC light, and on this filter you have the the viruses are like getting attached to the filter, and with the UVC light you can kill off the viruses. And then the air that is coming from the other side of the filter, it's basically clean and without living viruses. So, but in the future, what's getting more and more important is the water disinfection. So UVC treatment of water was already around for a couple of decades. But now it's more and more like starting to get interesting to do water disinfection using UVC LEDs. And I will also show an application example of this later. So typically most product designers have a challenge when starting with UVC LEDs, because in the past decades we had UVC tubes. Those have been around for a long time already, and those have a really high power. And so they were used all the time so far. But in the past few years, like fueled especially by the corona pandemic, the UVC LEDs got more and more powerful. So this is why the UVC LEDs are getting more and more interesting to replace the UVC tubes. So why do you want to replace the UVC tubes? Basically, the most the hardest constraint there is that they contain mercury. So basically, they have hazardous materials inside. So basically, when they break, you will have mercury flowing around in the room. So there is a goal to reduce the amount of products containing mercury. And so there's also a goal from the European Union to go there. So basically, in the future, we will see more and more switching from the UVC tubes to the UVC LEDs. So there are a couple of other interesting advantages. So other than the UVC tubes, those UVC LEDs turn on immediately. They are not shock sensitive. They are really small and can be therefore used in space sensitive applications. And the most important thing is that they don't have any hazardous materials. But the main drawback, yes, it is that they have a comparably low power. So basically what you need to do is when you start using UVC LEDs, you will need to figure out first if your LEDs are actually strong enough to achieve a disinfection. And this is what I want to tell you a little bit about later. So how does the UVC disinfection work? Basically, the energy of a single UVC photon is so high that it can split some special bonds in the DNA, and there we form some kind of dimers. So those thymine dimers, and basically this damage in the DNA hinders the cell from replication. So basically, if you have a bacterium with this DNA, it can't replicate anymore with this DNA. And the similar process also happens for the RNA of viruses, because as you know, viruses have just a single strand, not the double strand like the DNA. But basically, it's a similar process. So which wavelength is actually best for disinfection? There are quite a few studies here. And here is one study shown in black, the relative RNA damage depending on the wavelength for some kind of virus. And there you will find that the peak RNA damage that is induced is around 260 nanometers. There are a few other studies that show that some bacteria, they typically have a little bit higher maximum value, around 265 nanometers, but it depends very much on the germ and on the publication itself. So I also added the spectrum of one of our UVC LEDs in this graph. And what you see here is that our LED with 275 nanometer doesn't have the best wavelength to achieve disinfection. So why don't we use a wavelength of a UVC LED that is 260 nanometer? So why don't we use a 260 nanometer LED? Well, it's simply that the 260 nanometer LEDs and 250 nanometer LEDs, they are not as powerful yet as the 275 nanometer LEDs. So the technology for 275 nanometer is much more mature. And basically, I showed this in this graph, where you have the crosses, which are the relative wall plug efficiency, WPE, for different available LEDs on the market. And what you find is that actually the 275 nanometer has a much higher efficiency. So basically, wall plug efficiency it's the optical power divided by the electrical power. And you see, yeah, for other wavelengths, but 275, it's much lower. So actually, what you need to consider when doing disinfection is not only the wavelength, but also the efficiency of the LED, and also therefore the optical power of the LEDs. And when you consider both of this, you will end up with this gray dashed curve, which is the, I called it the relative sterilization efficiency, which is simply a product of the RNA damage and the wall plug efficiency. And you will find that this is actually peaking around 275 nanometers. So basically, currently, the 275 nanometer LED is still the best technology to achieve disinfection, simply because the technology is most mature. You have a better lifetime, you have a higher power, and then you get a better disinfection result. So the most common problems that designers have when starting trying to design UVC LEDs into an application is they have some kind of problem, like how do I disinfect the surface? But they don't know how many LEDs they need and where to place them and how close they can be to the surface and so on. Well, all of this can be modeled before starting to build prototypes. They can be modeled in optical simulation software. And this optical simulation software, you can use so-called WAV files to import in this software. Those WAV files, we offer them on our website. I will show you later where to find them. And those WAV files, basically, they give the three-dimensional directionality of the LED. So basically, as shown here in blue, those waves. So this is the content of those WAV files. It gives you the information how much waves go in this direction, how much waves go in that direction, and so on. And when you use those in the optical simulation software, you can actually simulate something called the irradiance. The irradiance, it's the amount of power received by the surface per surface area. So it's given in watts per square meter. Well, how can you get from this irradiance to the amount of disinfection? Basically, depending on the application you want a different amount of disinfection. So there's a nomenclature of how many germs were disinfected or were inactivated, and so this is called the dose. So basically, if you have a dose of D90, this means that 90% of the germs are inactivated. And if you have D99, it's 99% of the germs inactivated, so only 1% living, and so on. So depending on where your application is, you will need a different percentage of germ inactivation. And depending on this, you will need to change the amount of light that is hitting on your surface. So how can you achieve this dose? This dose is a property of some germ, so for example, for a virus and a bacterium, and it's a property of this special bacterium. And let's imagine we have a bacterium with a D90 dose of 18 watts per square meter, 18 joule per square meter, which is the energy per square meter. And if you have this germ on the surface, and you irradiate the surface with this irradiance and expose for 10 seconds, then what you will end up with is an radiant exposure of 18 everywhere where it's here red. And basically this means that everywhere where you have the red area here, you have like 90% of the germ inactivated that had this D90 dose of 18 joule per square meter. So basically, if you have another germ that requires a higher dose, then you will need to either increase the exposure time or increase the irradiance. You can increase the irradiance by adding more LEDs, or you are going closer to the LED. So as I mentioned, there are like this D90 dose is the property of different germs and viruses. It very much depends on the kind of virus or bacteria, and there are huge variations between different types of viruses. So you see, for example, the common coronavirus, it has depending on the study that looked into this, it has huge variations of the D90 dose. So some found only 6 joule per square meters, others found more than 100,000. So basically what this tells us is that actually the amount to kill, or the amount, or the D90 dose, it's not such a fixed value. It varies a little bit on the circumstances. So for example, on the surface properties where your virus is on, and so on, how much light you have on the surface, and how much reflection, and so on. So basically, it's really hard to give like a common value of a D90 dose, and to give developers a value to say, okay, this value is good enough for disinfection. Because as you see, it can vary a lot depending on the type of virus, but also on the specific setting itself. So, well, but to do a first, like to do some kind of calculations, we can start by using a median value, which is for the coronavirus, something like 37 joule per square meter. So this is what I will use later in the following slides to show how fast disinfection goes. And there's another value given by the German water disinfection norm, which gives which states that you need 400 joules per square meter of a radiant exposure in the water to have clean drinking water. So how fast can you actually achieve disinfection? Well, it very much depends on the amount of dose you want to achieve. So this is the amount of dose or the amount of radiant exposure. It's basically how much of the bacteria or viruses are killed, and also like which application it is. Here in this case, I show you like a UV panel, including 9 of our UVC LEDs. And I show you here on the left side the irradiance depending on the distance from the UV panel. So what you see here is if you increase the distance, the area that is irradiated is getting bigger, but also the maximum irradiance, or basically the irradiance value, it will drop down. So the further you go away, the longer it takes for disinfection. So you see this here, to achieve the dose of 37 joule per square meter, you like first at 4 centimeters, you need only like around 6 seconds. But if you go to 20 centimeters, you need already 1 minute. And this is some kind of a square rule. Like if you increase the distance by some value x, the time required to achieve a certain dose is scaling with x squared. On the other hand, if you want to achieve like a water disinfection from this 400 joule per square meter, this is actually much harder to achieve. So basically, you'll need a much longer time to achieve this dose to have safe drinking water. So here it's like already like 1 minute, or here 20 centimeters. it's already 11 minutes. So I also show you here an example of a water disinfection. That's just a simplistic model of a water disinfection device, where we have here on the left-hand side, we have quite a lot of UVC LEDs, and those all shine into this into the direction of the pipe, and the water is also flowing in this direction. And basically, what will happen? You will have a lot of light at the beginning, but as further away you go from the LEDs, the lower the irradiance is getting. So basically, you have less power or less watt per square meter if you go further away. So basically, what's interesting here is what can you actually achieve, or how much is the water flow capable of like going through this pipe with still having a sufficient amount of disinfection. So there's like behind this, I performed some simulations, and what you get from there, and you can calculate the amount of water flow that is possible to achieve a certain radiant exposure. So this is actually shown here in black, this curve. So if the water flow rate in liters per minute is increasing, then the radiant exposure is decreasing. So it makes sense. If the water is flowing through the pipe faster, then it's getting less irradiated by the UVC LEDs. So because it's a shorter time there. And then it's harder for this disinfection to happen. So this is why actually for really high water flow rates, it's really hard to achieve a sufficient disinfection or a sufficient radiant exposure to achieve this dose of 400 joules per square meter that is required by this German water disinfection norm. In this case here, in my simple case, what I received was water flow of something like 3 liters per minute was possible in this very simplistic model without like just having the LEDs next to the water pipe without any reflectors and fancy stuff. And basically what you find there is, to achieve the safe disinfection of above 400 joule per square meter, you need a water flow of below 3 liters per minute. So to put this into perspective, typical water faucets have a little bit, can maximally have higher values. So they can have something like 10 liters per minute or even 20 liters per minute. So this actually shows you already that the amount of water that is possible to be disinfected by UVC LEDs, it's still low. You can't use those UVC LEDs for like supply or like disinfection in a water supply for a whole village or so, because they are still not powerful enough. So you still use those UVC tubes, which are much more powerful. But basically in small applications where you have water dispensers, where you don't have so high water flows, actually there it's quite interesting to use those UVC LEDs already. So next, let me talk a little bit about UVC safety. As mentioned earlier, UVC light is able to actually damage part of your DNA. So this is actually a huge problem because these kind of damages can stay for quite a while, and basically it accumulates over time. And therefore, it's really important to be safe when working with UV light, and especially UVC, to have the appropriate safety precautions, like having protective equipment. And if you have used this in your application, the UVC LEDs, you want to shield the application completely so no light gets out of it. And also, if you have this application for some customers, you need to introduce some special safety measures so they can never be exposed to UVC light. There's also a maximum allowed dose per 8-hour workday. For the 275 nanometers, it's around 30 joules per square meter. And basically, to show you how fast you can actually get this maximum dose, I put again the example UV panel. There, at a distance of 4 centimeters, you can get this maximum dose of 30 joule per square meter already at 6 seconds. And if you go to even closer, even closer to the UV panel, you will get this maximum allowed dose already within a second. So this means already a really short exposure to those UVC LEDs can already exceed the daily limit, and it's dangerous. So this is why you have to be really careful when working with UVC LEDs. Okay, so let's jump back to the WAV files and our homepage. So this is how our homepage looks like. Here's also a link for it. What's most important for you to know is that under downloads, you will find the WAV files that I showed earlier that are needed for optical simulations. We have those WAV files available for the UV LEDs, but also for other visible and non-visible LEDs in our portfolio. So yeah, if you have any applications regarding where you could benefit from some kind of optical simulation, you can check out those other products and the other WAV files as well. And I want also to let you know that there's also an application note available also on our website stating, also giving an introduction of disinfection with UVC LEDs. So if you want to have some further reading, you can go ahead and look at this. Here are a few of my sources that I cited within the presentation. And I guess that's it from my side. And now I would be more than happy to receive any questions you have.
Yeah, so first of all, thank you very much, Dominik, for your interesting presentation. I found it very interesting. So yeah, as you have said, now we would like to turn our attention to the questions from the audience, and we've already got a lot of questions. So interesting topic also for our audience. So yeah, don't waste any time. We are starting into the next questions. And yeah, Dominik, there are studies suggesting 220 nanometer LEDs might be a safer solution for disinfection. Are they better than 275 nanometers?
Well, yes, there have been a lot of studies suggesting that 220 nanometers is actually potentially really good for disinfection, but it's also not as dangerous as the 275 nanometers, as those the 220 nanometer light doesn't reach so far into the skin. So basically, it's being absorbed already at the most outer layers of the skin, and therefore it's not reaching until to the places where you have DNA. So basically, it's being absorbed at the dead layer of your skin. This is why it's not so much dangerous. But actually, the technology for the 220 nanometers is still very immature. So you won't find any suitable LEDs that give you sufficient power to do some sufficient disinfection result. So yeah, there's still a lot of research going on in this direction. So basically, you will need to wait for a couple of years to get something there.
Okay, thank you very much. Yeah, then let's go on. Can UVC light negatively change the properties of plastic or other surfaces?
Yes, definitely, yes. So as the UVC light has a quite high energy, it can also split up some bonds in organic materials. So in polymers, there are few polymers that are more susceptible to the UVC light and than others. And basically what you will see when like irradiating those materials with too much UVC light, you will see some, for example, brownish like change of color. Then you will see cracks happening. Then you can see the integrity of the plastic will degrade over time, so it's going to be more like easy to break. So there's definitely some negative effect on this, but there's also some possibilities to go around this problem. Basically, whenever you use UVC LED light, you want to use as well materials that are not so much susceptible to damages. So you can use metals; those are not being damaged by UVC light. You can use some polymers that have UV absorber in them. So there are special polymers that are actually made for such applications. And there are also a few polymers that are more stable than others. So namely, for example, Teflon, and so all of those like highly stable polymers. So those are not so much affected by the UVC light.
Perfect. Thank you. Yeah, then just let's go on and we go to the next question. So yeah, as we have a lot of questions, just a hint, if we can't answer your question now in the live webinar, we will answer it later on via mail, or Dominik will do that. And also, if you have any other questions left after the webinar, you can also just email us at exhibition@we-online.com. So yeah, let's go on. What precautions should be taken when testing products with UVC LEDs?
Well, definitely you should be aware. You should have some kind of training in optical radiation. So you should be aware of like how light behaves, and that you can have, for example, reflections and so on. And you should also be when you do some product testing with them, you need to be sure that no light's coming out of the application. So basically what you want to do is use materials that are not transparent, so for shielding purposes. Then in the ideal case, if you want if you test products, you test them within like closed rooms or closed boxes. And also you can use like safety equipment, personal protection equipment. So they are like face masks or like face shields covering your entire face. And also you can use neoprene gloves and a lab coat, which is shielding the UVC radiation. So all of this can be done. But in principle, the best way to do it is always to have an application so safe that no light comes out. But if you can't ensure this, you should have some personal protective equipment. And there are different laboratory equipment providers that provide UVC safety equipment as well.
Okay, so thank you very much. Yeah, then let's just go on. Next question is, bacteria can develop resistances for antibiotics. Will there also be resistance to UV radiation?
So basically there have been studies that suggested that if you irradiate some bacteria for a long time with UVC light, they will start to have some selective pressure to be not so susceptible to UVC damage. And basically what they do, they simply increase their size, which makes the less UVC light come to the center or to the DNA of the bacteria. So basically, this is one possible mechanism that can happen. And basically, yes, there would be we would need a high amount of UVC radiation to kill them, but it's not like they are now completely immune against this, so they can't adapt this rapidly.
Okay, thank you very much. So yeah, then we have a look at the next questions. Yeah, Dominik, is there a D90 dose for inactive, already isolated DNA fragments?
If there's a D90 dose for already isolated DNA fragments. Okay, so this is, it's a hard question, because this D90 dose, as mentioned earlier, actually it depends on the type of DNA. Mainly this D90 dose depends on how many of those thymine dimers you can have. So basically it depends on how the DNA looks exactly. So this is why actually it depends on the specific type of DNA, and it's not so easy to say this, because it simply depends on the DNA, but not only, so it doesn't only depend on the outside of a virus or bacterium, but also on the DNA itself. So this is why I can't give you a clear answer to this.
Okay, thank you very much. Yeah, so another question, or Dominik, you can also pick a question if you see a good question, but we have a lot of questions.
Okay, yeah. So let me use this one. Are there any byproducts in the irradiation of air? I guess this comes from the question that, or like from the knowledge that some UVC sources, like the UVC tubes, then they can actually produce a little bit of ozone. So ozone is being produced when you have light that is also below 200, I think 40 nanometers. So but this also means that our UVC LEDs, which are 275 nanometers, they do not produce any ozone, because the energy of the light is not enough to produce ozone, and therefore you don't have any like byproducts happening in the air, like you would do if you would have 220 nanometer LEDs. There you would definitely have ozone as a byproduct, and then it would be really hard to actually use this product, because what will happen close to the LED, you will have a lot of some kind of small ozone layer, and this ozone layer actually absorbs the UVC light again, and so this is why then there's less UVC light actually coming out from the UVC LED in the end. But actually, this kind of process is also the reason why we can survive on Earth, because, the UVC radiation, it's dangerous, but it's not coming from the sun to the Earth's surface because of the ozone layer. So actually, this is actually also protecting us from this UVC radiation here on Earth. But yeah, definitely for some other UVC sources, this is a problem, ozone production, because ozone is also bad for our lungs. But for the UVC LEDs, you don't have those byproducts, no.
Okay, thank you. So also another question regarding the sunlight. Should 3D printers printing with UVC hardened filaments be protected from sunlight? Can you give an answer for that?
Okay.
It's a little below.
Okay, yeah. So I guess you have some kind of 3D printer that is printing some filament, some polymer that is hardened or that is cured by UV light. Basically, typically most of the printers, as I know, are typically the materials are cured with UVA light, not UVC light. So I haven't heard this before, to use curing with UVC light, because typically you use UVA light for this. But basically, if Yeah, this is a hard question for me to answer because it depends also very much on the polymer itself. So I can't give a clear answer here. So if it's like being cured by UV light, then it's a valid question. If then it's already also being damaged by UV light, I guess definitely if it's being irradiated long enough, then yes, probably yes. But it will depend on the material itself. Yeah.
Okay, the attendee says, okay, I see. Thank you very much again. And also, I think if there are any questions open at the end, yeah, just email us. Yeah, so I think then we are already at the end. We've done a lot of questions. There are some open questions still, but as mentioned, we will answer them, or Dominik will answer them later on via email. Yeah, so thank you very much. Thank you again, Dominik, for your interesting presentation and also for the Q&A.
Yeah, thank you all so much for listening.
Yeah, so now we won't give a hint for a next presentation because that was our last presentation. Yeah, we had really fun with you at our digital days and our virtual conference. It was really a pleasure with you. So yeah, thank you very much. Have a nice day, and I hope we will see us maybe in the next live event, live seminar, and yeah, maybe next year with the next digital days. Thank you very much. Bye.
Thank you. Bye.